Information theory is the scientific study of information, measuring how much information we have. Especially in machine learning, when we play around with the data set, then we want to extract some information from the data set. Okay, and the model will observe such information. So that's what we do. So information is quite an important concept in the machine learning. So in this chapter, we're going to talk about information and entropy, and we will define the KL divergence, and we will discuss some characteristics of KL divergence. And the cross entropy is quite important, the concept to define the objective function in machine learning. So we'll see that. And then at the end of this chapter, I'm going to introduce information flow. So first, before talking about the information theory and entropy, so we have to talk about the thermodynamics laws because there is a strong connection here. So in thermodynamics, there are two famous laws. The first law says the increase in internal energy of a closed system equals total of the energy added to the system, which means energy is preserved. Okay, so we cannot create energy out of nothing. Okay, that's the first law. And the second law says the sum of the entropies of the interacting thermodynamic systems increases. So simply entropies increases probabilistically. Okay, then what is entropy? So entropy is actually an expression of the disorder or randomness of a system. So when the system is well structured, then the entropy is low. And the system breaks down, then the entropy is high. Okay. And Albert Einstein said the two laws are the only scientific laws that are not changing in future. So scientific laws are changing. So scientific laws have been replaced by new ones. Okay, but Albert Einstein thought these two laws are the unchanging laws. Okay. Now let's talk about information theory. In science, we want to measure the amount of something, right? So before this information theory, we didn't have any way to measure the amount of information. But now we know how much information we have in a message or in a system. The idea is quite simple. Unexpected things have high information content. For example, if the sun rises tomorrow, then it is not news. That doesn't have any information because we already know that. But if the sun rises from the west, okay, then it is a big news because it is unexpected thing. And as another example, the Laplace's demon, he knows everything, then there is no news to him, so then he cannot add more information. That's another extreme case. Okay, this is basic idea about information. And Claude Shannon, who is the father of information theory, arguably, he defined information as a quantity, so-called Shannon entropy, in his monumental paper, Mathematical Theory of Communication. Okay, and first, he defined this degree of surprise, which means how much information is received when we observe a specific value. And as we said here, the information amount or the amount of surprise, the degree of surprise is proportional to the unexpectedness. The degree of surprise is defined in this way with the minus log. Okay. Now, entropy is actually an expectation of the degree of surprise, which is defined in this way. So the surprise was defined like this. Okay, and then we have expectation of this, which is the sum of the p of x times log px with minus here. And if the variable is continuous, then we can use integral. Okay, then when the P of x is 0. So this is not happening. The probability of this x is 0, then the entropy is 0. Okay, then what if P of x is 1? Then the P of x is 1, but log P of x is 0, then it is 0 again. So if P of x is 0, so we know this is not happening for sure, then there's no kind of information. If P of x is 1, so we know this is happening all the time, then this is not informative. Okay, and entropy captures the value of surprises as an expectation, and information from independent event is additive. So we have one event and there is another event. If these two events are independent, then two entropies are just additive. Okay. And the information is non-negative. In this equation, in this definition, the entropy is non-negative. It could be 0 or positive value. And entropy is an important quantity in the many scientific studies, like coding theory and statistical physics, machine learning, and so on. Okay, so for example, we can just calculate the entropy for binary case. So we have a coin. Usually the probability for head is 0.5 and the probability for tail is 0.5. That's normal coin, right? But we can imagine all kinds of coin with the probability P for head. So as an extreme case, the P of head could be 1. I never seen this kind of coin in my life, but let's imagine that whenever we toss the coin, then we will see the head. Okay, and also we have another extreme case. Whenever we toss the coin, then we will see the tail. Okay, but okay, anyway, let's imagine that. And we can imagine all kinds of coins between these two extreme cases. So usually 0.5 is normal coin. But we can imagine. And then this is the definition of entropy. And since we have two cases, head or tail, then the summation can be rewritten in this way. So now we can rewrite the entropy for the coin toss like this. Okay, and then the P could be 1, P could be 0, P could be 0 point something. Okay, then let's calculate this one. When the P is 0, then this is 0, 0, 0, so it is 0. So when P is 1, then this one is 0 and this one is 0, so it's 0. Okay, so we have a 0 here and this one is also 0. And when P is 0.5, then 0.5 times log 2 plus 0.5 times log 2, right? Okay, then it is log 2. And the base is 2, so log 2 is 1. Okay, now when the probability for head is 0.5, then it is 1. Okay, so this is how we calculate entropy. And when the event is more complicated, still we can do this. For example, if we play a dice, then we have 6 cases from 1 to 6. Then we can calculate this too. Okay, now let's get back to the thermodynamics entropy and the information theoretic entropy. So there is a strong connection. As you can see here, the thermodynamic entropy can be defined in this way by Boltzmann and Gibbs long time ago. And the information theoretic entropy is defined in this way. So if you look at these two equations are exactly the same except this constant. And this uses natural log, but in this case, it uses log 2. And many times the base is not that important. So basically, this one and this one, these two equations are almost the same except this constant. Now let's take another example from coding theory to understand how entropy works and why we talk about entropy. Okay, here is a task. So we have a discrete variable x to represent 8 possible states. And then the question is, how many bits do we need to transmit the state of x? So to represent 8 states, then if you are from the computer science, then you know the answer is 3. So we need 3 bits to represent 8 states, right? So we can actually calculate this number based on the entropy. So if all states are equally likely means it's something like a dice. So we have 8 states, so all the states have the same probability, 1 over 8 and 1 over 8 and 1 over 8. And then if we calculate the entropy, then this is 3. That's why we need 3 bits. Okay. And here's another a little more tricky question. Instead of uniform distribution, so instead of 1 over 8, if p of x varies as follows. So the first state, the probability is 1 over 2, and for the second state, the probability is 1 over 4, etc. So in this case, how many bits do we need to transmit the state? And let's calculate the entropy. And the entropy is like this. And if you calculate by yourself, then it is 2 bits. So which means we need just 2 bits. On average, we need 2 bits to transmit all the states, which is smaller than 3 bits. So we can save some network capacity. So we don't need the 3 bits on average. So how we need just the 2 bits rather than 3 bits? If we represent the first state with 0, and if we represent the second state with 1, 0, etc. Okay, then let's just calculate the average code length for one state. So this is the probability, and this is the length of this code is 1, and this is probability, and the length is 2, and this is probability, this is the length, probability, and the length is 4. And with this one, we have the same cases 4 times, so we just multiply 4 here, and then we need 2. Okay, so in the entropy, we calculated the entropy was 2 for this case. Look at this one. So the length of this one is connected to this probability. So if we design the code carefully according to this probability, then just 2 bits would be enough to transmit all the states. Okay, so actually the entropy is a lower bound on the number of bits to transmit a random variable. Now, to better understand the entropy, I want to talk about asymptotic property of entropy. So as distributions become more uniform, entropy goes up. So eventually, as an extreme case, the uniform distribution has the maximum entropy on a finite range. So when the x is between some range, then the uniform distribution has the maximum entropy, which means uniform distribution is most uncertain. Okay. And second, Gaussian distribution has the maximum entropy among possible distributions on an infinite range with a finite mean and variance. So the uniform distribution cannot be defined on an infinite range, right? So uniform distribution can be defined on a finite range. So among all the possible distributions on an infinite range, then the Gaussian distribution has the maximum entropy. So we want to prove these two things, but I'm going to just prove the first thing, and you can try the second thing by yourself. Okay, let's prove the first thing. Yeah, the uniform distribution has the maximum entropy distribution. So the proof is quite simple. Okay, so to find the maximum entropy distribution over the range A and B, then we actually define first the entropy. Actually, this equation is coming from the previous slide. Okay, and then since P is a probability distribution, then we have a constraint like this. And also we have this one too. And we're gonna use the Lagrangian multipliers. So this one, so we want to maximize this entropy with this constraint. So we have first term here, and then we have a constraint with the Lagrangian multiplier. Okay, so this is Lagrangian function. And as we did, and we're going to take a derivative of these laws with respect to this p of x and the lambda. When we take a derivative, then this one will be this. Okay, so you can think of this p of x as a vector. Okay, p of x is defined on this range, then this one is actually a vector, right? So if there is a range, then at this point we have some value and we have value. So think about this one as an array, then this one is a vector. Okay, so then we can interpret this term as P transpose P. Okay, that's it, right? Then simply the derivative of this one is simply P plus P transpose P over 1, so it is 1. So we get this part simply. And in this term, also you can understand this P of x as a vector. Okay, so instead of using integral, you can think of this one as, right. So if you take a derivative, then it is just 1, which is lambda here. So we got this derivation, and this one should be 0 if it is a maximum at that point. So it could be local minimum, it could be a local maximum or global maximum, doesn't matter. So at least this one is a local, to be a local maximum, then it should be 0. Okay, then we have only one possible distribution, which is e to the power of lambda minus 1. And fortunately, when we take a second derivative of these laws, then we get this one. And as you know, p of x is positive. And in this range, every point has positive probability. Then this one is positive, and this one is negative. So in total, this one is less than 0. It means L, the loss function, has maximum value, not the minimum value. Something like this. Okay. And this one is a maximum value because of this one and this one. So this one is maximum value. And if you take a derivative of this one with respect to lambda, then we get this one. And we already have a p of x in terms of lambda, so we replace this p of x with this one. And then if we solve this integral, then we got this one. So in this slide, what we did is we actually maximized this entropy with respect to p of x with this constraint. So when we maximize this entropy, p of x is actually defined by this one, which is a uniform distribution. So when we define a distribution over the range of a and b, then to have a maximum entropy, the distribution should be a uniform distribution. Okay, That's what we did. Okay, so maximum entropy distribution over the range of A and B is uniform distribution, like this. Okay, and if you want, you can prove the maximum entropy distribution over an infinite range is obtained by Gaussian distribution by yourself. Okay.